So a rose looks like the following sort of equation. You're going to have either r equal to something like, so for example, r equal to cosine of 3 theta. I'm going to warn you that my graphing skills here especially get a little bit less good. So we're going to also graph them on Desmos so we can see them. But so we'll graph this one kind of fully, and then I'll talk about how you can do it more easily. So if I was going to graph this, I'm going to make a table, okay, and I'm going to pick some values like theta equal to. So I want to get nice angles. So meaning I want like pi over 6 to show up. So I'm going to pick pi over 6. I'm going to pick like pi over, I guess pi over 18 seems too small. Let's do like pi over, let's do 0. How about starting at 0, James? Oh my God, sorry. So cosine of 0 is 1. And then I'm going to try and pick kind of the next place where cosine is either 0 or 1. So if I go to pi over 6, cosine of 3 pi over 6 is cosine of pi over 2, which is 0. So I can kind of see when I start to draw this thing out. Let's actually go one more. Let's go to 2 pi over 6, which is pi over 3. Cosine of pi over 3, or sorry, 3 pi over 3 is cosine of pi, which is negative 1. So we've kind of got already. So starting at an angle of 0, we've got 1. And then from 0 to pi over 6, we are getting smaller. So as our angle gets bigger, our values get closer and closer and closer to 0, like that. And then as our angle goes from pi over 6 to pi over 3, and again, I recognize it's not a very efficient way to do this, but this is how I want to see it to start off. So from pi over 6 to pi over 3, my values go from 0 to negative 1. So even though I'm in this direction, I'm actually in the opposite direction since my r values are negative. So I'm going to end up going positive 1. I should get a little ruler. I've got a little ruler. Yeah, ruler time. Cool. So we go this length here, which I should have made an actual length. Okay, it's like 1.5 centimeters-ish. Sure, yep. So we're going to go this way, about 1.5 centimeters. Sure. So the idea is that we're going to end up out there in that direction. So we're kind of going like this. There's where we've gotten to pi over 3, comma, negative 1. And then when we go from pi over 3 to pi over 2, well, cosine of 3 pi over 2 is 0. So we're going to get back this way. And the rest of this kind of plays out the same sort of way. Every pi over 6 is going to either end up at the end of one of our petals or back at the origin. So if I go another pi over 6, that's going to get me to 4 pi over 6, which is 2 pi over 3. And cosine of 2 pi is 1. So at 2 pi over 3, which is this angle up here, I end up being back at a value of positive 1. And then finally, coming in to the end, another pi over 6 gets me cosine of 15 pi over 2, which is 0. So we're back at the origin. And then finally, rounding it out all the way to pi, cosine of 3 pi is negative 1. So in the pi direction, which is to the left, our value is negative 1, which is going to turn us around and go to the right. So there is your 3-petaled rose. Couple things to observe. One, to get this 3-petaled rose, we have to let theta range from 0 to pi. 2, and this might not be very surprising, for r equals cosine 3 theta, that's not what I meant. The petals are evenly spaced. So each of these petals is kind of 120 degrees away from every other one, right? This main axis is theta equals 0. There's theta equals 120 degrees, or 2 pi over 3. There's theta equals 240 degrees, or 4 pi over 3. Now, what I don't want to do is draw a bunch more, but I will point out, like, you can totally draw this on Desmos. Desmos, you can totally just throw polar coordinates in there if you use r and theta. Probably if you do other things as well, but that's what I would do is use r and theta if this will ever open. Really? Come on. There we go. Wow, oh my God. This was great. Okay, so I will just point out. Remember that terrible integral I tried doing the other day in class? I started asking ChatGPT about how to do it. It was an interesting experience. Like I was doing a volume with ChatGPT and it like did it mostly right, but got wrong. I'm like, I think your limits of integration are wrong, and then it like fixed this. So it was interesting. It was curious. What's that? No, the like the AI chat thing that people everyone's talking about. Like it can do math problems, kind of. Why not? So if we graph r equal to what was it, cosine of 3 theta? Backslash there. And then you just type in the word TATTA, yeah. There might be another way to do it, but that's the easiest way I know how to do it. And then you can pick your range for theta. So they've given me the correct range that I want, which is 0 to pi. But if you go from 0 to 2 pi, it'll double back on itself, which you can't really see. It does. So yeah, kind of neat. Also, if you want to make things more easy to see what's happening in a polar sort of way, you can go up here and change your grid to be like this. That makes it a little more obvious as to what's going on. It's kind of cool. Yeah.
So if you branch tree to some even number or odd number, higher number, will you add to the pedal?
So that's actually a good question. So here's what I'll say. More generally, so let's actually graph one more, and I'm not going to actually graph it well. Yeah. So if I was going to graph r equal to sine of 3 theta, here's how I would actually graph it. I would know a couple of things. I would focus my lens. So I would say one, I know that I'm going to have 3 petals evenly spaced. They're always going to be evenly spaced. And my job at that point, once I know how many petals there are and that the spacing is even, is to figure out where they live. And so for odd numbers of petals, I'm just going to figure out which one is on axis. Because you'll always have one that's on either the positive or negative x-axis or the positive or negative, y-axis. And the easiest way to do that is just to let theta equal 0 or theta equal pi over 2. One of those two will give you an on-axis value that's not 0. I could have done that for cosine as well, right? If I pick theta equal to 0, that exactly gives me that point there. Theta equals 0, r equals 1. And then I know once I've got that one there, which is as far away from the origin as it can be, because the biggest cosine can be is 1, then the other two are going to be going in those directions here. So for this one, if I let theta equal 0, that's not helpful because I'm getting r equal to sine of 0, which is just 0. If I let theta equal 2 pi, and then we get r equal to sine of 3, sorry, I said 2 pi, I'm going to say pi over 2. 3 times pi over 2, and sine of 3 pi over 2 is negative 1. So what this tells me is that in the pi over 2 direction, which is up, my r value is negative 1, which is the opposite direction, down. So there's where one of my petals ends, or has its furthest point, and then the other 2 petals are going to be that way, right? 120 degrees in either way. So this one's going to be at pi over 6. This other one's going to be at pi over 6. And then
the way to do this without showing that much work, right?
Right, exactly. So I'm trying not to do all the work in the world or make a table, as some people might be very against.
That makes me just confused on like how much, but no, what you're doing is
Right.
what my professor said, how much work I should be doing.
Now, I will point out, if you actually, I remember, I think when I used to use like my TA calculator and you could change it to polar coordinates and it would like graph it out, it would graph it out as theta increased, right? So it, like if I was actually graphing this out in the order that theta increased, it would start here and it would go like this way, and then this way, and then this way. Right? That's actually how the graph gets drawn out as theta goes from 0 to pi. which I don't know if we need to know, it's just kind of interesting. I should ask you all, have any of your teachers talked about finding the area using, like doing an interval using polar coordinates? Cool.
Basically, it's just parametrics.
Okay.
We need that.
Yeah, okay. So yeah, we won't sweat it too much because it's fine, it's kind of a pain. So here's what I'll say. For petals, sorry, for roses with an odd number of petals come from either r equal to sine of n theta or r equal to cosine of n theta, where n is odd. So if you have r equal to sine n theta or cosine n theta, you're going to get n petals evenly spaced. And just find where one of them lies on either the x or the y axis. So just for example, which I'm not going to draw, but I will tell you that if I was going to try and graph, say like r equal to 5 cosine of, why did I pick 5? I don't know. 5 cosine of 7 theta, I would start by letting theta equal 0. That gives me r equal to 5 times 1. So I know that my rose is going to have 7 petals. And one of them is going to be on the positive x-axis, right there. It's going to look kind of like that. And then the other 6 of them are going to be evenly spaced. And they shouldn't actually like overlap on each other, like would probably happen if I tried to draw it. Because it's so let me show you, right? Let me show you on Desmos. Okay, yes. So instead, if we make this r equal to 5, whoops, that's really big, cosine of 7 theta. And so there is your rose with 7 petals, evenly spaced, right, around the origin. They do get skinnier. There's actually an interesting question on the on this handout talking about how you can find the area again, which requires the other thing we haven't talked about in the roses. There's a neat little formula that happens for no matter how many petals you have, which is kind of interesting. But yeah, they do get skinnier because they have to kind of fit each other in. Now, it's slightly different for an even number of petals. So if r equals, yeah, let's do sine. Let's say we want to do sine of 2 theta. Oops, you might want to see what I'm writing. Let's make it 3 sine of 2 theta. All right, I'll graph this one as well. So typically when I'm graphing something that I know is a rose, I'm looking for the values of theta that either make r 0 or r as big as possible, meaning 1, or I guess the value 1 or -1. So here are the values I might pick if I was going to plot this would be, well, I want 2 theta to be either 0, pi over 2, or pi, or 3 pi over 2, or 2 pi, etc. So theta should be half of that. So the angles I'm actually going to think about are 0, pi over 4, pi over 2, 3 pi over 4, pi. And then sine of 0 is 0. Sine of pi over 2 is 1. So I get 3. Sine of pi is 0. Sine of 3 pi over 2 is -1. So I get -3. Sine of 2 pi is 0. So I start graphing this thing. At the beginning I get 0, and then my angle is pi over 4. I get 3. So kind of going out this way. And then when my angle is pi over 2, right? So when I go from pi over 4 up to theta equal to pi over 2, from here to here, my values are getting smaller. So I'm going back towards the origin. And then when I go from pi over 2 to 3 pi over 4, my values are getting, did I do that right? Yeah, that's right. Yeah. My values are getting negative. So even though my angles are pointing in this direction in quadrant 2, I'm going to go in the opposite direction in quadrant 4 because my values are negative. So I'm going to be going out to this point right here. Theta equals 3 pi over 4 and r equals -3. And then I'm going to go back to the origin again. And you might notice it doesn't look like all of a flower, all of a rose, right? I should be missing half of it. And so to get the other half of it, we have to go to all the way to 2 pi for our angle theta. So we're going to go this way. And then finally this way. Again, graphing skills notwithstanding. So for when your n is even, so if you have r equal to cosine of n theta or r equal to sine of n theta, and n is even, we have a rose with 2n petals. So right here, we had sine of 2 theta and we got 4 petals. If you did sine of 4 theta, you'd get 8 petals. If you did sine of 6 theta, you'd get 12 petals. And interestingly, I think it's interesting, the cosine one has petals that are on axis. So if it was cosine of 2 theta, all the petals would be on the coordinate axis. If it was cosine of 4 theta, you'd have them all evenly spaced out and you'd still have 4 of them on the axis. Whereas sine, on the other hand, never does.
That would only be for 2 theta, right? That's only way when it's above.
Well, no. So what I'm saying here is that, like, no matter what even multiple of theta, cosine will always be on and sine will always be off.
But how could you put 6 theta?
Sure, let's take a look. So let's say we had cosine of, well, let's just do the small one. There's cosine of 2. It doesn't look very symmetric, I gotta say, right? Or at least from my perspective. Doesn't it? I guess it does. I think it's really just my perspective that's skewing it. So there's cosine of 2 theta. Do I want this 5 here? Yeah, I kind of do. Let's see what happens if I make it smaller. Just trying to get it like, no, about the same. Doesn't really matter. Okay, sure. But then if I make that 4, now my 8 petals, they still get the ones that are on axis, and then the other ones are evenly spaced. Or 6 theta. I get 12 petals, still on axis, still evenly spaced. Whereas if I do sine instead, off axis, essentially the on axis rotated 45 degrees, off axis, off axis. So it's just the same as the cosine one, just rotated so that essentially the petals are in the middle of where they were before. Yeah. Yeah, definitely. Yeah, fair question. Right. Although, so I will say that I would say yes, that is true. The only time where I think about that kind of not being true is when you're talking about like powers of functions. Sometimes I'm still going to think of like x to the 2/3 as kind of having an even nature because the numerator part's even and the denominator part's odd. So sometimes you apply it to fractional powers, kind of, but yes, to answer your question generally, yes, even and odd really only applies. Then things are terrible. And then we get graphs I don't want to graph because they're really weird. For example, if you graph like theta over 2, which I think was one of the questions we were doing. But the thing is here's the problem. My theta didn't get big enough. Or if you do theta over 3, yes, it'd be really weird. And you go bigger, nope, 2 pi is I guess all I need here. I think it's 3 pi. So it's kind of weird. Sometimes you need to let theta go all the way to 2 pi. Sometimes you need to let theta go all the way so that the angle you're actually taking your trig function of goes all the way to 2 pi, but sometimes it's only pi. You just kind of keep going until it starts to repeat on itself. So yeah, it's kind of weird. So here's what I'll say. Roses, fine, they're very straightforward. They do what they do all the time. The other kinds of graphs I think you should be aware of are the following two. You should definitely be aware of something like r equal to 6 cosine of theta. That is a circle. And since it's cosine, it's going to be on the x-axis. And here's what I would do. I'm going to plot 2 points. So plot when theta equals 0 and theta equals pi over 2. When theta equals 0, cosine of 0 is 1. 6 times 1 is 6. When theta is pi over 2, cosine of pi over 2 is 0, and r equal to 0 is always just the origin. And those points there are the ends of a diameter of this circle. So here's my circle. Starts here, goes this way. There's pi over 2, and all the way out this way, back to pi. So we get the full circle as theta goes from 0 to pi. And I think I talked about this a little bit last time, so I'm not going to spend too much time on it. I will just point out that you could totally show this as a circle if you didn't like doing it this way by actually converting to polar, to rectangular. You could take r equal to 6 cosine theta, multiply both sides by r. So r squared equals 6r cosine theta. Wow, can I write cosine? Maybe. And then r squared is x squared plus y squared. R cosine theta is 6x. And then if we bring the 6x over to the other side, you've got x squared minus 6x plus y squared equal to 0. Complete the square. So add 9. And then you've got x minus 3 squared plus y squared equal to 9, which is a circle centered at 3, 0. With a radius of 3.
Just curious, because the thing I've been doing polar coordinates,
Mhm.
is basically just transform it to x equals r cosine theta and y equals r sine theta.
Right, exactly.
And then just- that doesn't look all the time.
Oh, ooh, no, that doesn't work all the time. I see what you're saying. Yeah, that doesn't really work here per se.
Why would you-
Well, like, so how would we do it?
say x equals, and then r would have to be 1 over r, so that would be.
Right, exactly.
Okay.
Right. It's not so what you're saying specifically is for a circle that is centered at the origin, typically typically just a unit circle.
So you're very limited to only some of the polar coordinate problems?
Yeah, like so because what you're saying is if you want to describe a circle, you can use parametric equations very easily to just but that's really that it's not that it's restricted, it's just that it works best for circles that are centered at the origin. Writing this parametrically is much more difficult. What I'll say is when you have r equal to 6 cosine theta, or in general, r equal to a sine theta, or r equal to a cosine theta, you're always going to get a circle. This is going to be a circle centered on the y-axis. This is going to be a circle centered on the x-axis. And of all the graphs that come up, I would say this is the one you're probably most likely to actually use in the future. The last one I'll point out, maybe not the last one, but the last one I think that's kind of standard to be aware of are cardioids, which are kind of a pain. So kind of the standard nicest cardioid you're going to see is one where you have, well, I will say generally, first of all, the general equation is going to be something like r equal to a plus b sine theta, or r equal to a plus b cosine theta. And the quote unquote nicest cardioid are the ones where A and B are equal to each other. Actually, they're equal to each other in absolute value. Meaning, I don't care if one of them's positive or one of them's negative, they're both the same sign, it doesn't actually matter. I think. Yeah, that's right. Yeah.
That's what you said.
Yeah. So for example, I could graph something like R equal to -2 plus 2 sine theta. And that's kind of your ideal cardioid because it's got the nice perfect shape. So here's what we're going to get. For the perfect ones, I'm just going to plot my usual favorite 4 points, 5 points, I guess, where theta is the nice quadrantal angles. 0, pi over 2, pi, 3 pi over 2, and I guess 2 pi again. And so then my R is going to be, well, sine of 0 is 0, so I get -2. Sine of pi over 2 is 1, so I get -2 plus 2, which is 0. Sine of pi is -0, so -2 plus 0. Sine of 3 pi over 2 is -2, so I'm going to get -2 plus -2, which is -4. And sine of 2 pi is 0, so -2 plus 0 is. This one's a little weirder than usual because I got a lot of negative R values. That's okay. So 1, 2, 3, 4. Okay, so let's see here. So when my angle is 0, I'm giving -2. When my angle is pi over 2, I'm going to get 0. When my angle is pi, I'm going to get -2. So I'm over here now. When my angle is 3 pi over 2, I'm going to get -4. So up here, when my angle is 2 pi, I'm back to -2, which is again over here. So I'm going here, then here, then here, then here. This is going to have the usual shape. This pen's starting to go. Well, except, it's symmetric. Let's compare that to what it actually looks like. Again, polar coordinates especially, I feel like, are hard to draw, or maybe that's just me. So -2, was it? Yeah, plus 2 sine theta. Yep, there's your usual cardioid. Now, what happens when you start changing the relationship between these two numbers is it deforms in one way or the other. So if you make this a little larger in absolute value, it kind of does that. And depending on how large you go, check this out. It's kind of flat, and then maybe it gets even weird, right? You can kind of, it's interesting, I think. That's still a cardioid. It's just, it looks very circular almost.
It's like the sign has less than enough impact.
Right. That's an excellent way to say it. I love that. On the other hand, and what's even weirder is if this number gets smaller, then you get weird loopy things. Yeah. So what I have noticed is that specifically, basically, it deforms in one way or the other. So if the absolute value of A is, I have to think about this for a second, smaller than the absolute value of B, we get a loop. And if it's the other way, then it deforms the other. I would say it gets fatter, I don't know, longer, bigger, it gets bigger. Or what Patrick said, the sign has less of an impact. It becomes more.
You say it gets more like circular?
Right, well, because let me put it this way. If we did away with the 2 sine part, which is the part we're saying is less impactful, we'd be left with R equal to what? Just whatever number we pick, right? Which is a circle. So I think that's actually a really excellent way of saying it. If you have R equal to some really big number plus a smaller multiple of sine or cosine, that sine or cosine part isn't going to have as much impact. And so you're just going to get the more circular part. I like that. I've never heard it said that way before. That's an excellent observation. Thank you, Patrick.
So the only way to know how circular or like flat it is, like graph it.
Yeah, I mean, and again, even then, it's, I mean, graph it by, when you say graph it, I mean, use a utility to graph it, because my actual graphing of it is. So here's what, right, so like if I was gonna graph a cardioid, here's what I would do. I would still pick those same 4 points. So if I was gonna try to graph something like R equal to, I don't know, like 2, no, not 2. Sure. 2 cosine theta plus 5, for example. So I know, so here's how I know I don't get a loop. They don't have other solutions where this is equal to 0. Right? If I try setting this equal to, well, in fact, I don't have any solutions where this is equal to 0. If I try setting this equal to 0, I get cosine theta equal to -5/2, and we know that has no solutions. On the other hand, the reason our previous example hits the origin exactly once is because -2 plus 2 sine theta equal to 0 has exactly one solution between 0 and 2 pi. The one solution is when sine of theta equals -1, or when theta equals 3 pi over 2. And then just to fully go with this, if you have something like r equal to 2 cosine theta plus 1, that's going to have a loop because you're going to hit the origin more than once. When you set this equal to 0, you get cosine theta equal to -1/2, which has 2 solutions. We actually happen to know them here because it's a nice value. You get theta equal to 4 pi over 3 and 5 pi over 3. This is where you get your loop. But for this one here, the way I would actually try to graph this is just by plotting the usual 4, or I get, yeah, 4 points is correct. So when theta equals 0, I get 2 plus 5, which is 7. When theta equals pi over 2, I get 0 plus 5. When theta equals pi, I get -2 plus 5. And when theta equals 3 pi over 2, I get 0 plus 5. So typically, cardioids have symmetry about the axis of the trig function that they go with. So you should always be thinking cosine kind of goes with x, sine kind of goes with y. So if my cardioid is r equals something times cosine plus a constant, it's going to have symmetry about the x-axis. If it's r equals something times sine plus a constant, it's going to have symmetry about the y-axis. So then you do your best to. So here's what I would be thinking of, right? This is the biggest it gets, so we're getting smaller. So as we kind of go this, right, as our angles go this way, our values are getting smaller until we get to this point there. So right, so it should be a little bit bigger here. Well, right, we're getting kind of bigger. And again, it's not perfect, right? I'm just kind of this. It's really not perfect. Yeah. And then from here, we're still getting smaller. So we're kind of coming in this way. It's probably like that. It's probably something like, but not exactly like that on the top half. And then I would love to draw the bottom half just by copying it, flipping it over, but instead I actually have to draw it. So, okay, maybe, let's compare. Make ourselves feel less good about our graph. If we compare this to 2 cosine theta plus 5, let's see what we get. Yeah, it's an okay job. I think the hard part for me, honestly, is recognizing, like, I kind of want to come into this and hit it like with a horizontal tangent there, and that's wrong. Like I really want, I would have, if I wasn't paying attention, I'd have been like, oh yeah, it's gonna come like this, and right there it's gonna have like a horizontal tangent, and then we're gonna go in real quick like that. And that's not the right way to see it, because we should be thinking, oh yeah, I'm further away from the origin as I move towards this angle here. It's not an exact, I mean, you can be exact with the calculator, but like as far as drawing these by hand, it is not an exact science. The one, so I'll give one more example here. So just to kind of talk about these loops. So if I was going to graph 2 cosine theta plus 1, here's how I would graph it. And then we'll look at that one you were asking about last time. So I'm still going to pick my usual 4 points. I'm still picking theta equal to 0, pi over 2, pi, 3 pi over 2. There's no need to write 2 pi because we know it's the same angle as 0, and it's going to give you same value. And then R is going to be 3, 1, -1, 3, 1. So when I start plotting things here, it gets a little weird. So there's my angle is 0, my value is 3. Here's my angle is pi over 2, my value is 1. Here's my angle is pi, and my value is -1. So when all the things on the axis of symmetry are on the same side, that kind of indicates I have a loop. And then finally, 3 pi over 2, I'm going to get 1. So here are my 1, 2, 3, 4, and then 5 points. And I kind of have to hit them in order. So I have to start here, and then hit that, and then hit that, and then hit that. So here's what we get. A loop like that. Now, the way we actually kind of see that is by saying, oh yeah, if we set this equal to 0, we end up getting the angles where theta is equal to 4 pi over 3 or 5 pi over 3. Oh, sorry, not 5 pi over 3, 2 pi over 3. I misspoke. Apologize. 5 pi over 3 is in quadrant 4, which would make cosine positive. So I should, that's wrong on the previous page. Which makes sense when we think about it. So right here, we're going from 0 to pi over 2. And then from pi over 2 to pi, we hit the angle 2 pi over 3, which is where we hit the origin. So pi over 2, 2 pi over 3, pi, 4 pi over 3, 3 pi over 2, 2 pi. So kind of interesting.
So it's 0 at 4 pi over 3 and pi?
Nope. So let me just label things here. So here's the angle theta equal to 0, theta equal to pi over 2, theta equal to both 2 pi over 3, and then here's where theta is equal to pi.
Oh.
And then again, we're back here and at 4 pi over 3. And then here we're at theta equal to 3 pi over 2. And then finally, here again, theta equal to 2 pi. Okay, so then there's all sorts of weird things. And I don't really have, I'll be honest, I don't really have a good way to explain how to draw things other than what I think you should do. What I would do is just a table and start thinking about things that are going to be bigger or smaller. But it's funky. So there was one, and what was it? Was it r squared equal to 2 cosine theta? I think that's what it was. Yeah.
Yeah.
We were talking about this one yesterday. 2 cosine theta.
Yeah.
And so here's how some people like to do this, and it's not incredibly wrong. It's not wrong at all. But so like, for example, just to go back to this example for a second. If I was trying to graph r equal to 2 cosine theta plus 1, what I could have done, which is not wrong, it just is very different. It's never a way I thought of it. That doesn't mean it's wrong. I just have to think about it. So if I was graphing 2 cosine theta plus 1, I'm going to graph it on the xy axis first. So here's my theta, here's my r. So I'm shifting it up 1, and the amplitude is increasing by 2, or is multiplied by 2. So I still have my usual period from 0 to 2 pi, but now going up 1, and then my amplitude's 2. And then I'm going to try and make this look good. I mean, I always try and make it look good, extra good. So cosine starts up here, and then hits right here, and then down here, and then up here, and then back to here. Yeah, sure. Good. So what we can then do is we can take that and kind of translate that to a polar coordinate situation, right? We're saying, okay, well, when theta is 0, I'm getting a value of 3. And then as I go from 0 to pi over 2, I go from 3 to 1. So pi, right? So 3, and then smaller, 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 smaller. So I'm gonna end up kind of like that. And then from there to there, I'm actually gonna go, right, so right here, although I didn't draw it very well, that's my 2 pi over 3 angle. And so then when I get to an angle of 2 pi over 3, I have to come in and hit the origin. And then even though I'm gonna be in the third quadrant, my angles are, or my values are negative. So I'm actually going backwards, or actually, even though I'm still in the second quadrant, sorry, from 2 pi over 3 to pi, I'm still in the second quadrant. So my values are over here. And then that's where I hit pi, and then I'm still having negative values, right? There's pi. So then from here to here, I'm still going to get negative values, but now they're in the third quadrant, but they go negative. So they're in the first quadrant. And then I finally get back to being positive. So here's my 4 pi over 3, which points, this way. And now I'm going to get slightly larger and larger values. So I get to 1. And then finally in quadrant 4, getting bigger and bigger and bigger again. Like that. I don't love that, but it's something people do. So we were talking yesterday about how the teacher was doing that for this. So what they did was they graphed r equal to plus or minus the square root of 2 times the square root of cosine of theta. Which is just weird. Because first of all, you're very limited what theta can be. Theta has to be in quadrant 1 or in quadrant 4. Because that's the only places where cosine. Again, I mean, right, you could go 0 to pi over 2, 3 pi over 2 to 2 pi, then you can go 2 pi to the next, right? You could go further, but if we're just thinking from 0 to 2 pi, then we're really limited to just being in here in quadrant 1 and over here in quadrant 4. And so then, I really don't like this. So then if we plug in 0, cosine of 0 is 1, and root 2 times 1 is root 2. So we're either up here at positive root 2, or down here, because r can be plus or minus, be negative root 2. And then as the angles get closer to pi over 2, cosine gets smaller. So we do something like this. And I know my graph isn't perfect, right? Maybe it's not the form enough. But then the other part of this should look the same. It's kind of flipped, so we're kind of doing this. So, right, these are the R values, these are the, so then we're taking that, which now, again, seems super funky, and translating that to actual polar graphing. So when I start at theta equals 0, well, my radius can either be positive root 2 or negative root 2. And then as theta gets closer and closer to pi over 2, so as I move in this direction, my values either get closer to 0 this way or closer to 0 this way. So,
It's so weird.
right? So if I just look at this part right here, I'm saying, okay, well, bigger, and then so as my angle increases, my R values are getting smaller. So I'm doing something that's kind of like that, but it's not like a perfect circle or half circle or anything. It's just, I'm just making it up. And then in a similar way, from there to there, my R values are getting less negative. So, right, my angles are this way, but my values are that way. So it's kind of like this symmetrically. And then over here, same deal. If I start at theta equal to 2 pi, I'm getting the same values, but then if I go that way instead, right, going back, so starting here and going in that way, my angles are going this way, and my R values are getting smaller. So I'm kind of doing the same thing. It was looking okay. I don't know. It's a whole kind of do your best situation where graphing these is terrible and try to do the best job we can. Yeah, I mean, I would say don't spend too much of your energy worrying about polar. I know we just spent a whole class talking about polar coordinates, but like that said, they're mildly important when you talk about polar and sphere and cylindrical coordinates in 21D. When we start doing volumes and three-dimensional intervals and stuff like that. But we're not going to see them all next quarter. So try to remember them. I know throughout next quarter, and then whenever you take 21D, maybe next fall, maybe over the summer, if you have to take it. Polar coordinates eventually be like, oh yeah, there were polar coordinates once upon a time. Yeah, they're really useful for describing circles.